So our last problem in chapter 9 asks us to think about bond polarity. And I'm going to give you a simple way to think about bond polarity that for most of the cases that you are going to encounter is going to work just fine. You need to ask yourself a question. When you're looking at two atoms that are bonded together and you're asking the question, is this bond polar? Just simply ask yourself the question, are these two atoms different? If the answer is yes, they are different. As long as they're not carbon and hydrogen, you have a polar bond. So let's kind of write this down. So the question you need to ask yourself is, are the two atoms that are bonded different and not carbon bonded to hydrogen? If the answer is yes, that means your bond is polar. And this is an important thing to point out. The fact that a carbon-hydrogen bond we don't consider to be a polar bond. Okay, so here's three that we want to look at. We've got nitrogen bonded to hydrogen, we've got fluorine bonded to nitrogen, and we've got iodine bonded to chlorine. So again, in this case, we just need to look at whether they're different, and in this case, nitrogen bonded to hydrogen. They're two atoms that are different. They're not carbon and hydrogen, so yes, this is a polar bond. This problem asks us to use a polar arrow to indicate the polarity of each bond. Well, polar arrows simply look like this. They look kind of like an arrow with a cross over the tail. And what that does is it points to the most electronegative atom. So it points to the more electronegative atom. And it reminds us that that's going to mean that there's a little bit of a positive charge remaining on the other atom because the covalent bond isn't shared equally. So in this case, nitrogen is more electronegative than hydrogen, so this bond is going to point in that direction. For fluorine and nitrogen, remember my electronegativity boogie in class, right? My boogie points to the most electronegative and then least electronegative atoms on the periodic table. So fluorine, being the most electronegative, is going to have this arrow pointing in that direction. And again, electronegativity is a trend. If we draw the trend for electronegativity, it increases as we go up and it increases as we go across. That's how I got my electronegativity boogie, is I pointed to the most electronegative spot in the periodic table and the least electronegative spot. So looking at two atoms that are bonded that came from the same group, right? Chlorine and iodine. We know that chlorine is going to be more electronegative than iodine because it's higher up on the periodic table. So in that case, we can draw our polar arrow in this direction. So that's all that we needed to do for problem A, was actually use a polar arrow to indicate the polarity of each bond. The next part asks us to rank polarity of bonds. And in this case, we're going to have an atom that's the same, which is hydrogen. So hydrogen bonded to nitrogen, hydrogen bonded to oxygen, and then hydrogen bonded to carbon. It's really too difficult to do apples to oranges comparisons here. Like I couldn't really give you a hydrogen to nitrogen bond and then say, an oxygen to chlorine bond. Something like that really wouldn't work. There's too many things that you're comparing here. So in this case, we're looking at the differences between these, right? If we were to draw our polar arrows, we'd always draw them away from hydrogen. Oops, in this case, this is nonpolar. We'd always draw them away from hydrogen when we have a more electronegative atom. So again, when we're looking at these, we can see that we're comparing three atoms that are in the same period. So oxygen, again, is going to be more electronegative because that's our electronegativity trend. So that means that that bond is going to be the most polar bond. So if we're ranking these bonds in terms of increasing polarity, the oxygen-hydrogen bond is going to be the most polar. And we just talked about carbon and hydrogen bond we really don't consider to be polar at all. So the carbon-hydrogen bond is going to be the least polar, followed by the hydrogen-nitrogen bond. So these are in terms of increasing polarity. And if we want to think about percent ionic character, okay, and if we want to rank them in terms of decreasing ionic character, a way to kind of think about this is that the most ionic character is going to come from the most polar bond. Okay, so if we think about the greatest ionic character is going to come from our most polar bond, which is going to be our hydrogen-oxygen bond there. So that's got the most ionic character. The next comes from hydrogen bonded to nitrogen, and then hydrogen bonded to carbon. So again, ionic character really refers to how unevenly are those electrons shared, right? And the greater the difference in electronegativity, the more greedy one molecule, I should say one molecule, one atom is for those electrons than another. And again, if we continue to kind of move across this trend here and kind of move over and grabbed metals and then nonmetals from the periodic table, we'd have an unequal distribution of electrons that's so great that we actually become an ionic bond. It's not even sharing anymore because somebody is so greedy for those electrons. Okay, so pretty straightforward. Not a lot of sample problems actually from Chapter 9, but lots of opportunity to apply a lot of these principles as we move on to Chapter 10.